we are going to start to look at basic circuits. So we're going to start looking at circuits this week. All right, we're going to look at circuits this week. And one of the aspects about circuits that we're going to want to learn is how to create proper diagrams of the circuits. Now, the picture you see at the upper right is maybe a physical setup of a circuit. You have a battery, you got a couple wires coming out, going to your resistor, you got something going out to your capacitor. That may be the physical setup of the circuit, but when we draw our circuit diagrams, we create a more simplified picture. We generally don't want to draw a physical setup of the circuit because it will introduce a lot of extraneous information that's not relevant to the circuit. And it's much more easier to read your circuit diagrams when you just sort of have a standard sort of way of displaying things. Your circuit diagrams are not physical, they are logical, basically. The basic logic of the circuit is there. It may look different. For example, you see your battery in the middle and the picture in the top. When we look at the bottom here, we have the battery on the left-hand side. But the circuit still works the same. Notice that the resistor and the capacitor are both hooked up to the terminals of the battery. Therefore, that is a parallel configuration, and the logical circuit drawn down here shows a parallel configuration of a resistor and a capacitor. So that's the idea of the circuit diagrams. Now, there's a lot of symbols that you're going to see to represent our circuit elements. This is a very standard way to show like a power source, in particular a battery, having these four lines here, labeling positive and negative. The computer says something bad's about to happen. And then it stopped. Okay. Sometimes I just get lazy, to be honest, and I'll just throw a picture of a battery in there. But if I do have a symbol like this, though, generally what you want to have associated with that is the EMF symbol, little cursor V. A wire is indicated with a straight line, of course. A junction is indicated, which looks like a junction where this line splits. Now, resistor is any element that has an associated resistance to it. And if it's just a generic resistor, it has this dashed line here. Okay. A light bulb indicating a circuit is a resistive element, but the light bulb is meant to highlight the power being generated by the current. So sometimes you'll see a bulb listed, that just means resistance, but in particular it's trying to highlight power. Capacitor looks like a couple lines like this. Switches look like a switch. And you'll see some other circuit elements as we move along in our journey of studying circuits, and I'll introduce those as they come. All right. Now, the EMF of the battery here, you can label this with the number of volts it is. A positive and negative terminals are labeled. However, you will notice that the picture sort of implies that because the longer line's on top. And but still useful to have that in there. I mean, the purposes are twofold. One, you're drawing something that clearly labels it as a power source, and you want to make sure that looks different than just a capacitor. You know, you think, well, why do I have to have four lines? I could draw two lines. Well, two lines look like a capacitor, actually. So you want to draw the four lines out here. But I'm okay if you draw a battery symbol, except if you're moving on and you're taking more complicated circuit classes, don't do that because they might laugh at you, just be honest. So, all right. So, question for you here, letter in the chat. Got a light bulb connected to this battery here, what's going to happen to this light bulb? All right, B, this light bulb would not light because we have not drawn, well, we have not indicated a complete circuit. A complete circuit has got to be a circuit that clearly connects from the positive to the negative terminals of the battery, and this does not do that. In fact, the way the light bulbs usually work is there's a connection on the side and then a connection on the bottom, and that completes the circuit. But there's nothing connected to the negative terminal of the battery, not a complete circuit. So that's definitely something you want to keep in mind when you draw, because you're going to draw a lot of circuits here on out for a while, and it's very important that when you step back and look at everything, that you can make sure that you go from the positive to the negative terminal of the battery to make sure you have a complete circuit. And it's also important to realize that there's circuit elements that are not connected the way they should be. Okay, every circuit element in some form has to be connected to the battery, right? I mean, it has to be, basically what I'm saying here is current has to be able to flow. Okay. So this is an example of a complete circuit. It's about the easiest circuit you could possibly imagine. You got your battery, which creates your potential difference going from negative to positive. We loop around, we get to a resistor, which will experience a potential drop. Now, because these are the only two circuit elements here, the potential gain by the battery will be equal to the potential drop by the resistor. That does make a couple of assumptions. One, we've already discussed, that wires are ideal and they do not contribute to any potential drop that will occur in your circuits. And the second thing, which we might explore either, I don't know if we do it today or if we do it on Wednesday, but the battery is considered to be ideal. The reason why I say that is because batteries are not ideal. When your batteries wear out, they have a particular potential difference that they're supposed to perform at. And what happens is over time as they're used, they develop an internal resistance to them that effectively reduces the potential difference that exists in the battery. So sometimes we will include that, but in this particular case, we're not doing that. Okay. Now, when we analyze our circuits, there's a lot of things we need to keep in mind. Some of these ideas we've discussed before, but I'm going to bring them up again because we're specifically going to start applying them now. We have Kirchhoff's junction law that states when you approach a junction in a circuit that the currents that go in must equal the currents that go out. And that is for charge conservation. It actually becomes an equation. One of the things you're going to see here is that solving circuits involves creating a system of linear equations that you solve. So if you're the kind of person that likes to solve linear equations, we'll have great news for you. We're going to do a lot of that stuff. If you're one of those weird people that likes to create a matrix for every single system of equations, no matter how easy they are to solve, we'll have good news for you. You can create as many matrices as you like. Fill your heart's content. All right. So, the other law that we're going to work with is the loop law. Now, when it comes to loop law, you choose a location in your circuit. It doesn't matter where that location is. It could be near the battery, it could be away from the battery, anywhere. But the idea is that when you start at a particular location in a circuit, you can loop around. So you basically travel along the circuit until you get back to the same point. And the idea is that as you travel along that loop, any potential differences that you occur, when you sum those up, they're going to have to equal zero. Now, when I say you loop here, it's any possible loop that you can make. It could be the whole circuit, it could be part of the circuit, it could involve the battery, it doesn't have to involve the battery. Any loop works. Any loop works. So, in fact, let's go back for a minute here. Let's go back. Okay, look at this diagram here at the bottom. How many loops are there? Somebody. Tell me.
Are there 3?
3. How many loops are there now? Let's put in a resistor here. Zzz, that's my resistor. How many loops are there?
Are there 8?
I believe there's 6. Large. We got the 3 in the middle. We got the 2 on the left, and then we have the 2 on the right. That's 6, right? There are 6 loops in this diagram here, and you can choose anything you want for loop law. Again, we have the big one. We have the little ones, 1, 2, 3, that's 4. The 2 on the left and the 2 on the right. 6 loops. Now, that means you can make 6 equations. Should you do that? No, not really, because you actually will develop a lot of redundancy. You'll get a redundant system, which can still be solved. It just creates a lot of work for you. So, for example, it doesn't make sense to create, like, for example, if I did, let me erase what I have here. If you did the whole loop here, the whole thing, and then you did just the left-hand side, that's not very helpful. There's some redundancy there. I mean, if you were to do all 3 equations, the big loop and the one on the left and one on the right, well, the one on the left and the one on the right are basically the same thing as the one that's the larger loop. So, you only have to make, remember, when it comes to solving a system of equations, you only need to make as many equations as you have unknowns. If you have 3 unknowns, you just need 3 equations. You could have a 4th. I don't know, you're just making more work for yourself, but maybe you like to solve systems of equations. I don't want to stop you. Go for it. I could send you systems of 10. We can write some Python code to solve systems of 200 or 1,000 equations. That could be fun. That's actually a good linear algebra thing. They don't teach you that. They should. But they don't. They just teach proofs. They don't teach anything practical. Anybody wants a good linear algebra textbook that teaches you some useful skills, shoot me an email. Send you a free textbook. That's awesome. All right. So, when we want to draw, proofs are cool. Don't get me wrong. I mean, I minored in math, and my minor in math was I had to take 3 extra classes, and I took the junior level analysis series, which is completely idiotic. It's like the hardest 3 classes I could take to get a math minor. But I like the proofs too. It's just that most of you don't like proofs, and most of you kind of want, your education to be more practical. So anyway, all right. So we're going to be solving circuits here. When we solve our circuits, you want to make sure you have a diagram, and I highly recommend you draw lots of diagrams for things. In fact, I will tell you right now, okay, if you had before 110, I had a rule in 110. If there are forces in a problem, there needs to be a free body diagram. If there's no free body diagram, assuming it's not like really simple, gravity down, normal force up, and that's it. Well, okay. But anything more complicated than that required a free body diagram. If you didn't have it, the problem's wrong. This is true here too. Okay, if you're presented a circuit, obviously you don't have to redraw it, although you should. But you have to build a circuit in a problem. If you have to draw something out, you have to do it. I got to see a circuit there. Okay, if I just see a bunch of equations, no. Draw your circuits. Draw. Okay, very important. So, now when you draw your circuit, you want to use all the symbols that you know. And ultimately, you have to sort of determine how the current flows in your circuit. Well, here's the good news about that. You can do whatever you want for that, as long as it's logical. Okay? For example, let's go back a little bit here. Now, it's maybe a little silly right here, but, you know, let's say current comes out of the battery here, the positive terminal. We're reaching a junction here. Now, does the current go down and then to the right? Could it go, you know, into the junction here, and then the right side goes into the junction, and then things go out the bottom? Maybe. Here's the beautiful thing about this. You can guess wrong as long as it's logical. For example, you can't say that all three currents at the junction go in. That's clearly wrong, right? But it's possible that the horizontal ones go in and the bottom one goes out. That's logical. That's possible. And you can guess that in your circuits. And if you're wrong, what happens is when you solve for your current, you'll get a negative sign. And all that tells you is you did it right. Well, I don't know. Maybe you could have done it right, but your current should have been in the other direction. Okay. So once you make a decision about current, then you have to figure out how to express your potential differences. Now, here's how it works. If you travel through a battery from negative to positive, that's always a potential increase. Okay. Now, if you go backwards through a battery, that's a potential drop. Okay. For resistors, if you go in the direction of current, that's a potential drop. If you go against the current, that's a potential gain. We'll do a lot of examples of these, so you make sure that you can understand what's happening here. But there's sort of two ways to discuss directions in circuits. You make a decision about how the current flows, and then you make a decision about how you're going to walk through your circuit for your loop law. Okay, let me go over it one more time. If you go from negative to positive terminal of the battery, that's a potential gain. If you go from positive to negative, that is a drop. If you go with current on a resistor, it's a drop. If you go against current, that's a gain. Okay? So, let's talk about one right now. What do you think's going on with the current through this resistor here? We happen to have two batteries. We have a 3 ohm resistor. What do you think is the current going to be through this resistor? And I'm going to step away for a minute because I need my drawing pad. And I don't know where it is. I think I do. But put a letter in chat. I'll be back in like 15 seconds. C's? D's? I think I like D. I think I like D. It's C. I hope I'm right. It's D. Let me prove it to you. I'm going to do this in two ways. The first way is this. I'm going to make a decision. The first thing you do when you want to analyze the circuit, you want to make a decision about which way you think the current goes. And I said which way you think it goes. You can get that wrong. I'm going to assume that my current here goes, and I'm going to draw it like this. I'm going to call that current just I. Sometimes you might see people do something like this. Well, not with that little funny line out there, but they draw like a little, you know, like an arrow that's rotating, you know, to indicate the direction there. Now, when I do my loop law, here's how we do loop law. You have to make a decision about where you start. I'm going to start down here in my lower left corner. Why? Because I just want to. It doesn't matter where you start. You start anywhere you like. Let's do it, though. Let's do my loop law. I don't know why it does that line. I'm not happy about it. All right, so as we walk through the circuit, we're going with the battery. That's a +9. We go with the current through the 3 ohm resistor. Now the potential difference, remember, for a resistive element is the current times the resistance. So that's going to be here a negative 3I. Okay, it's negative because it's a potential drop. I'm going with the current. And the resistance is 3, and the current's unknown. And then I come around to the 6-volt battery, and I'm going against the battery. So that's a minus 6. And set that equal to 0, and you solve for I. As you can see here, you'll get a positive 1 out of this. Amp, right? Amp.
Why is it a minus 6?
Because we went against the battery. We went from the positive to the negative. Because we're going clockwise in our circuit here. Going clockwise in the circuit. So we went with the 9-volt battery, but we went against the 6-volt battery. Right. Now, let me do it differently. Let me go, did you do this picture here? Let's say that we didn't go that way with the current. I mean, it was a guess. It was a good guess. The reason why it was a good guess is because you can see your 9-volt battery is stronger than the 6-volt battery. So that's likely going to dictate, excuse me, the current. But let's say, you know, I don't care about that. I'm going the other way. Nobody's going to tell me what to do. I'm going to go this way. And I'm going to do the same loop log. I'm going to start in the bottom left-hand corner, and I'm going to walk around. Okay? The 9-volt battery is still positive 9 volts. Because it doesn't matter about the current. It's what are you doing? Are you going with the battery or against the battery? It has nothing to do with the current. Okay. Then, you see, I'm going against the current when I go through the resistor. So that means this is a 3I. And that's for the resistor. Because normally it's a potential drop, but I'm going backwards through the resistor compared to the current. So that's not a drop, that's a gain. And then when I go through the 6-volt battery, I'm going from positive to negative, so that is a negative 6 here. And if I solve that, and I solve for I, you get negative 1 amps. So what that is, that's science telling you, yeah, you can make your own decisions, but you're wrong. Okay, we were wrong. The current does not go counterclockwise, it goes clockwise. Now, what would this mean if you're solving this problem here? You don't have to redo the problem. All you got to do down here is once you get down to the negative, you make a little statement where you accept what the science is telling you. I accept I made a mistake, and I'm okay with that. The current apparently goes the other direction. You don't have to change anything in your problem, though. Of course, if this is the first step of a larger problem, you should make a little note saying, I was wrong. And then, of course, as you move on to the other parts, make it a positive and know which way it actually goes. So that's what you should do. And of course, you'll see a lot more examples as we move on here. But that's just an example if I wanted to be stubborn and say, I'll do my own thing.
Real quick, could you, for the procedure for going clockwise, was that negative 6 still negative 6?
Yeah, because
Okay.
the batteries don't care about the current. The batteries just care if you're going with them or against them. When you deal with resistors, you have to compare how you're traveling to the current direction. If you go with current, it's a drop, you need a negative. If you go against it, it's a gain. So in this case, it's a positive 3 because I'm going against the current as I travel in my loop. Now, what I should do here is I put a little notation, and I'm going to say here, you know, where am I going? I'm going to go clockwise. Oops. You know, I actually might say, you know, clockwise loop. You know, I have a little indication down here, clockwise loop, you know that. What are you smiling about? Being sneaky. All right. We'll do more. We'll do more. Don't worry. Okay. Well, I already said all this stuff. Yeah. I already said all this stuff. All right. What is the potential difference across the 10 ohm resistor? Now, this is leading into a discussion here. So let me know what you think. I don't think you people know. I don't think you know. Let's do it. Loop law. I'm going to start in the bottom left-hand corner. That's my favorite corner. Bottom left. Not in this circuit, just in life. Bottom left corners are fantastic things. The current. I'm not going to be a dum-dum here. My current's going to go as the clockwise. I don't know why I don't know why it does that line thing. I got to figure that out. Hope it's not a little bug or something. This thing wasn't cheap. So let's do our loop law. I'm going clockwise. Positive 30. I keep walking. I take a right turn. I take another right. I see my 10 ohm resistor. So that's 10 times I. I see my 5 ohm resistor. 5 times I. Remember, for the resistors, do an IR. That equals 0. Now, the current here is 2 amps. Positive, got the direction right, and then you go back and you realize that the 10I and the 5I represent your potential drops. So that means this is 20 and this is 10. And loop law is obeyed now because the battery caused it to increase by 30. Apparently, the 10 volt makes it drop by 20 and the 5 makes it drop by 10. And so we go around the loop and everything adds up to 0. And we got it. Okay, so the answer is B. There we go. Okay, so again, you make a decision about which way the current goes. You can get that wrong. That's fine, as long as it's illogical. Then you choose a location to start a loop. Once you have that location, you travel around any way you like. Any way you like. You get back to the same point and you record all of the potential differences. It'll create an equation that has an unknown. Solve for it. You got it. Any questions about this so far? How about you, Barky? You got it? He seems pretty happy. So I think Barky's good. Okay. Now, one thing that is of great interest to us is that, you know, a big part of circuits is their, you know, I mean, we talked about current, that was related to potential difference, which means there's energy involved. So that means we can talk about power, how the energy is delivered. Remember, power is energy per time. So if we want to talk about the power that is supplied by the battery, that is going to be given by I times delta V of the battery, which we just call E. Now the reason why this exists is because, remember, we have a potential energy term that we use. And that potential energy term, yeah, sure. Let me go back. Walter had a great question here. How do we know that the resistor is positive or negative? It depends on how you walk using the loop law. Now, I decided in this problem here that my current, in the circuit was clockwise. That means the current is going down like this. And if my loop, that's current, And if the loop that I take has me go the same direction as the current, those are potential drops. You'll put a negative for the potential difference. If my loop, for whatever reason, goes opposite the direction of the current, they are positive. That's how you know. So, what about power? What was potential energy? Remember the definition of that? U equals Q delta V. You get me. Nobody gets me, but I appreciate the sentiment. All right, potential energy is Q times delta V. Well, guess what we do with this thing? Take the time derivative of both sides. Time derivative of the energy will be power, and the time derivative of charge is current. So therefore, we have our nice expression here, I times, now it's delta V, but when we do delta V for a battery, we use the little cute squiggly E for EMF. Power, as you know, is in watts. Oh, the derivation's right here. Whatever. Okay. Now, oh, this is for a resistive element. It's the same derivation. If it's a resistive element that you're working with, then the delta V is for the resistor. So we don't have a little funny, cute, squiggly symbol for that one. It's just delta VR. But there's a lot of ways to express this. For example, we can have I delta V, or we can use Ohm's law here and rewrite delta V so that the power is now I squared times R, or use Ohm's law to get rid of the current, and delta V squared over R is also. There's three different expressions you can have, and you want to think about all three depending on what the problem is. For some reason, for example, if you're dealing with parallel configurations, we know our delta V's are the same. So that helps you compare power in elements that are in parallel. That's helpful. So anyway, it just depends on what the application is and what's more useful to do. So let's talk about this a bit more now. I don't need to talk about this. You already know this, right? I don't need to talk about that. Which resistor dissipates more power? What do you think about that? Which resistor dissipates more power? A lot of A's. A lot of A's. A lot of A's. Uh-oh. Got a B up in here. It's B. It is B. All right, so we're going to use the power expression that involves delta V. Now, this is a parallel configuration. They have the same delta V. So, for power, it's delta V squared over R. The resistor on the right is smaller. It produces 9 times the amount of power than the one on the left. Now, if you said A, I'm very happy that you said A, because you're going to learn something. Having a higher resistance does not mean more power. Power is ultimately generated. Oh, no. Okay, so here's the logic. Here's another way to think about it. Because we can analyze this circuit, right? We can analyze the circuit and we can figure out exactly what's going on here. In fact, how much time do we got? Because I got a lot of slides today. I don't have a ton of time, but I'll just kind of briefly describe it. And I encourage you at home to work on this on your own here. But think about this. Here's another expression for power. Not that. I squared times R. Now, one of the things that you're going to learn here is that the current is going to come out of the battery and it's going to branch, right? It's going to branch proportionally to the resistances. The greater the resistance, The greater the resistance, the less current it's going to pull. In fact, in this setup here, I said proportionally. And what's going to happen is the current that flows through the right-hand side is going to be 9 times larger than the current on the left-hand side of the two resistors here, right? That's Ohm's law, right? Delta V, I times R. They have the same delta V's. So if one has 9 times the resistance, then the other one pulls 9 times the current. And look at the relationship for power. It's current squared. So the fact that the 1 ohm resistor pulls more power is a much bigger factor. Because you can look at this expression and say, oh, well, look at R. Right? It's linear with R. Well, okay, but in a parallel configuration, it's complicated to think about how current is going. It's better to think about delta V, because delta V, that's the same. Now, if this is a series configuration, the current's the same through the resistors. So it actually made me more helpful to think about I squared times R. All right. So if you said A, excellent. So, ready? Here's the next question. Which resistor dissipates more power? The 9 volt or the 1 volt? Let me know what you think. Letter in the chat. The answer is B. Hey! Everybody first said A. And then we talked about it. And we did it again and you got it and you got B. That's called learning. You just witnessed learning right there. It's somewhat intangible. Well, you just saw it firsthand. We learned. Yes, it's the same question. But you got it right this time. You learned. Now, are you going to remember it in 2 days? No. And there is the pitfalls of learning. Retention. All right. Which has a larger resistance? A 60-watt light bulb or a 100-watt light bulb? Now, there is an assumption here. The assumption is you plug it into basically the same outlet. So your delta V is the same. Just to be clear, it's a light bulb. You live in a home. Your home, hopefully your home isn't weird. I don't know how you would do that. You'd have to have some kind of special transformer. So maybe you shipped your home from, France or something. And you got to have some kind of funny transformer to convert your electricity. I don't know. That would be strange. But it can happen. A's, huh? Well, I must say, I'm a little surprised at all your A's. But I'm going to chalk that up to... I mean, it's true. If you just took a house from France and just brought it over here, you want to hook it up to the grid, you'd have to have a transformer right outside in your box. Because they don't do the same. They do things differently over there. It's not American current. It's not American power. It's some, whatever you want to call it. All right. Yeah, I'm really glad. A lot of you said A, and that's fantastic. That is right. If you're bringing your I'm assuming you're bringing your whole house with you. Your appliances and everything. Yeah, you could your outlets, right? In fact, I don't know the details here. Like, I'm assuming the wiring works the same. They got the same kind of wire in there. No, they don't use 60 volts. Don't they use 210? I thought. Maybe I'm wrong about that, but Europe voltage. I thought it was like 220 or 210, 240? No. Really? Yeah, it's 220. It's 220. Yeah. So, like appliances got to work a little differently. If you have DC converters, you don't have to worry about it. It's all the same. So, the 60-watt light bulb has a larger resistance. Because if you're hooked up to the same outlet, right? If the power is lower, it's because the resistance is higher. Okay, so your 100-watt light bulb is more sort of efficient. It makes sense that it doesn't have a large resistance. Okay, we couldn't produce that much power if the resistance was actually higher. All right. I'm very happy you all got, I mean, I don't know if you all got it, but I saw a lot of A's. I saw a lot of A's. Let me go back. It was all A's, basically, which is fantastic. Because when I normally ask this question to my other classes, you know, back in the day, didn't go so well. But I was really pleased about that. Yeah, well. Okay, so now, man. Okay, so in terms of energy production, there is another unit that you've heard about. You know, if you're paying bills, pay an energy bill. You know, one way to specify energy, we use joules, right? But kilowatts, thousands of watts, right, is power times a unit of time does correspond to energy. Kilowatt hours are actually the way that at least Edison, I'm pretty sure all energy companies work this way, charge for power. You can, at any given time, you can go out to your meter, and you can see what your kilowatt per hour usage is averaging. Most meters display that information. And you can get a sense of, I mean, really what you can do is if you can really control what's going on in your house. Like I did this for my air conditioners, you know, let the air conditioners go, record kilowatt hours, turn them off, and I get a sense of basically every hour I use my air conditioner, how much that's costing me. And it's something crazy like $1 an hour. I mean, that doesn't sound like a lot, but I mean, if my air conditioner's running 12 hours a day, for example, you know, you got 30 days, that's hundreds of dollars. So, but average cost of electricity in the United States is 10 cents per kilowatt? I don't think so, not anymore. It's like double that at least. I think I pay like 21 or 23 cents now. I don't know. They forced me into the Lancaster stuff, which actually is cheaper. Surprisingly, I don't know how it is. Actually is a little cheaper. That's nice, but anyway. All right, so great example here. Oh, actually, I have an example later. Never mind. Let me do an example. I think is it the next slide? No, it's not. I think I do it later, but I'll talk about it later. Anyway, so let's look at some examples of power here. Cut out for a minute there. All right, so let me give an example here. It's a little puzzle to think about. The top circuit has a battery hooked up to a single light bulb. So when we switch out that light bulb, when we put two in parallel here. All right, so in the example here, we got these two light bulbs hooked up, and the current that passes through them is going to be less because what you have here is you have effectively twice the resistance. Everything set up in series here produces effectively twice the resistance, and as a result, only half the current gets pulled here. I love the desert. Love it. I love living up here. People always crap on this area. I love the AV. I think it's awesome for the most part. You got meth heads. I mean, it's like a character thing. You know, you go to Walmart, you just enjoy the scenery. It's just funny. You know? Just kidding, I never go to Walmart. Anyway, all right. So, if you have a series resistor set up here. The idea, of course, is when you go through these resistors, you get potential drops. Now, the principle here is this. The same current has to pass through both resistors. Okay? They pass through both resistors. Then, when you work out the math here, you get IR plus IR. You can factor out the I. And what we find here is that resistors in parallel, there is an equivalent resistance to them as if they were combined into a single one. Now, note something about this, though, which is a little obnoxious, I'll be honest here. Series resistors get their resistances added. You remember capacitors in series? You didn't add them. It's the exact opposite for capacitors and resistors. And the reason why is because for the capacitor, it's Q equals C delta V, and resistors have, I mean, how would I put it here? The relationship between the voltage for the capacitor and the resistances are different. So you have different relationships there. It just comes from the nature of the two equations here. So series resistors add up. Okay. And as many of you have in series, you add them all up. So, what is the current in this circuit here? D, oh, it is D. I was like, D? You idiots. No, it's D. The equivalent resistance is 18. So 12 over 18 is... Let's talk about this one here. A lot of examples here. What's the voltage drop across each resistor? What's the current out of the battery? Draw a graph of voltage going around. Okay, do I have examples? I guess I don't have many examples today. Let me share this with you all. Okay. So, series resistance. Easy enough. Add them up. Equivalent 27. Your Ohm's law, you apply Ohm's law to the equivalent resistance. We get 9 over 27, which the current is 1/3. So it's very easy to figure out the potential differences. You simply do Ohm's law for each individual element, right? So you're doing 1/3 times R for each of these. You get 5, 4/3, and 8/3 respectively. Add them up just to make sure it equals 9. Loop law is obeyed. I have a graph here. It's kind of crude, not a big deal, but that's how we do this. Okay. Now, this is what I was talking about earlier. Real batteries, right? Real batteries. So the idea with a real battery, if we don't want to assume we have an ideal battery, is there is an internal resistance that develops in a battery. Which, what it does here, if we just apply a really simple relationship here, acts as a resistor. And we subtract off from the EMF that we use a lowercase r for the internal resistance. As you can see here, this is going to result in a potential difference in the battery that's actually a little bit lower than it's supposed to be. And as I mentioned, this is what happens when you have your general cell batteries that wind down after a while. The internal resistance builds until it no longer reaches the threshold that's required to make whatever particular equipment you have work. Okay. So when if you're going to solve a circuit like this, you basically consider the fact that your internal resistance is in series with, say, another resistance. Like in this example here, our internal resistance is going to be in series with a regular load. So it's almost like the load has a higher resistance, you can say, so we just treat that as an R plus R. And then we can figure out our... You have a problem with that, at least on either this homework or the next homework. So now a short circuit is an example of a circuit where something happens in your circuit and you're disconnected from much of the load in your circuit. And in that sense, the current ends up being driven extremely high because it would only be based on whatever internal resistance exists inside the battery. So this generally happens if you screw up making your circuits, if you have damage to your circuits. For example, if water gets in and things are not properly shielded, water can act as a conductor, and that can short out things. But when we say the word short circuit, we basically mean it's a circuit where you bypass a lot of the other aspects of the battery, which means you're bypassing a lot of loads, which again means that you're driving a lot more current than you probably would be doing. That current's based on the internal resistance of the battery or any potential loads that are still in the way. But it definitely tends to make the current much larger, and it could actually cause the battery to, wear out faster than it normally would. All right, so example of voltmeter here. A voltmeter is something that, as it sounds like, it measures the potential difference across a circuit element. Right? So measure a difference across a circuit element means that you want to create a device that can read the potential difference across a circuit element, but does not affect the behavior of the circuit. That's the idea. And the way that's done is voltmeters generally have an extremely high resistance to them. And when we put them in parallel with our circuit element, this junction doesn't really do anything. Because if the effective resistance of this voltmeter is insanely high, it's not going to draw any current. And so it doesn't affect the overall behavior of the battery, and we simply read what the potential difference is. Because, again, a parallel configuration means the potential difference across both is the same. For an ammeter, the opposite is true. To read the current traveling through a particular branch, we're going to have to put an ammeter in series with another element, because the current is going to be the same as it passes through both. The ammeter has to effectively have an extremely small resistance, again, so it does not affect the overall behavior of the circuit, and it will be able to read what the current is, since it's not really going to affect much. Okay, so another puzzle here. We have two light bulbs initially in series here, and there's a current that goes through. We like to know what happens when we close the switch. What happens when we close the switch is that light bulb A will become brighter. It will become brighter. Light bulb B will actually decrease a bit. And then, of course, light bulb C gets brighter. And the reason why is because when A and B, now say these are all identical things. When A and B are connected in series, we have a certain current coming out. Let's just say the resistance of A and B and C are all 1, right? 1. So that means the current comes out of the battery, and it goes through A and it goes through B. Right? The overall resistance would be 2. Now, if we close a switch, the overall resistance of the entire network becomes 1.5, because B and C will combine together to have a resistance of 1/2, because they're in parallel. Combine that with the series configuration for A, and we have an overall smaller resistance. So that means more current comes out of the battery, goes through A becomes brighter. But then the current has to split at the junction, and B and C share that new current, but that will be lower than what the current was originally. It's a good exercise if you'd like to do this on your own, but when you close the switch here, A gets brighter, B gets fainter, and obviously C turns on and matches what B is. Excellent, excellent thing there. Puzzle. Okay. Parallel resistors. The potential difference is the same across both. So if I want to figure out what the I could say the junction here, right? Coming in has to equal the currents going through each branch, right? So I have this relationship here that I equals I2. I1 plus I2 are indicated with Ohm's law. Now, because it's a parallel configuration, the potential differences are the same, so it can be factored out. And we have this nice expression over here, which indicates we're adding inverses up. So just like for capacitors, we have a similar relationship here, although this applied to the series configuration for capacitors, this applies to the parallel configuration for the resistors. The equivalent resistance is the sum of inverses, the inverse of the sum of inverses, right? And if you have a lot of those together, that just ends up with resistance here. Okay, so don't put a letter in the chat here. I'm just going to get through the rest of this. In this example here, we have a 12 and a 6 in a parallel configuration. Let's figure out what the equivalent resistance is there. 1 over 12 plus 1 over 6. Flip that. So these two here apparently have an equivalent resistance of 4 ohm. And so that means the current that's being generated here, delta V over R, is 12 over 4, or 3 amps. That's what's coming out of the battery here. Now, 3 amps is going this way, but guess what happens? It starts to branch. 2 amps go through 6, and 1 amp goes through 12, because the current has to split proportionally. If the resistor on the right has 1/2 the resistance, it will have twice the current. So what will eventually happen here is this gets 2 amps, and this gets 1 amp.
Sorry, Professor. Where'd you get the 4? Which was like 4 ohms. Where'd you get that from?
That's from doing the parallel configuration, 1 over 12 plus 1 over 6. Take the inverse of that. That's how you get your 4.
Oh, gotcha.
The parallel configuration way you do that.
All right, thanks.
All right, I got 2 more things here. We want to know what the equivalent resistance of this setup is here. Now notice it's a complicated network of resistors, and the rule is when you have you work with the innermost one and you go work your way out. What's going on here? Well, I'm going to start with layer 1 and then work our way in. Layer 1 is a 20 ohm resistor in parallel with a whole bunch of things on the left. Okay, let's look at the left. The 42 ohm resistor is in series with a bunch of things in the bottom. Let's look at the bottom. The bottom are 3 parallel resistors. This is going to be, where's my little marker here? Okay. 1 over 60, 1 over 60, 1 over 45. And in fact, I should just show my slide here for that. All right, so the 60, the 60, and the 45 are in parallel. You add their inverses, take the inverse, we get 18 ohms. The circuit now, well, at least this combo breaks down to a 42 and an 18 series, which is in parallel with 40. We combine the 42 and the 18 in series, we get a 60. Now we're at the final layer here, the outermost layer. The 60 is in parallel with the 40. 1 over 60 plus 1 over 40, we end up with 42 ohms. So the entire network behaves as if it's a single resistor of 24 ohms. And that's what we're looking at there. Okay, last problem. We want to rank the bulbs in order of brightest to faintest. The assumption here is they all have the same resistance to them. Okay, so what happens is this. We come out of the battery and we have a junction. Now, more current is going to go out of the junction toward the lesser overall resistance. If we assume everything is, say, 1, for example, that means Q and R will combine in parallel to be an equivalent resistance of 0.5. Combine that with P, it's like an equivalent resistance of 1.5. The right branch are two things in series. We can add them up and say 2 ohms. Now, what I said here is I'm making the assumption everything is 1 ohm. I can say whatever I want, though. So that means more current's going to run through the middle branch than the one on the far right, right? Because there's less resistance in the middle. So P is the brightest. Then S and Q have equal brightnesses, but they're going to be the second brightest because when you get to Q and R, the current has to junction and branch off and split in half. And that will ensure that not only Q and R are equal, but they will be less than S and T because of the branching of the current that's there. So the correct order is P is greater than S equals T, which is greater than Q equals R. And again, the easiest way to see this is just to imagine they're all 1 and just work things out from there.